All right. So 1-1 is about patterns and inductive reasoning and deductive reasoning. So 1-1. Patterns, inductive and deductive reasoning. So we'll start off kind of easy. We'll start with some patterns. For example, you've seen these before. Like SAT tests. Here's a couple of numbers, figure out what the pattern is, and find me the next three numbers in this. It's called a sequence. 13, 16, 19. Now, how did you figure that out?
Add 3.
Well, it looks like if you add 3 here, you get to 4. If you add 3 here, you get to 7. If you add 3 here, you get to 10. So the implication is, to get to the next 3 numbers, you just keep on adding 3. Woohoo! Is that the only pattern that would work with those numbers?
Yes.
You think? No. More than likely, I could probably find another one that would have those first 4 numbers, and I can come up with 3 different numbers and a different type of pattern. It would be a lot more complex than just adding 3, though. That's the only problem. But I could probably make one. How about something almost as simple? Oh, this one's real simple. And I want the next 3 numbers. 16 goes to 8, 8 goes to 4, 4 goes to
0.
0. How do you get 0? I'm just curious.
I subtract 4 from each one.
If you subtract 4 from 16, that brings you to 12.
No, 8.
Yeah, but it has to work from each step of the way. So if you subtract 4 from
divided by
16,
2 is 8. 8 divided by 2
divided by
is
2.
4. 4 divided by 2 is 2.
all right. So 16 divided by 2 is 8. 8 divided by 2 is 4. 4 divided by 2 is 2. Next number? 1. Next number? Why do people keep saying 0?
1 divided by 2.
What's 1 divided by 2? 0.5, or also known as
1/2.
a half. You're not getting to 0 this way. Dividing by 2 will never give you an answer of 0, unless the top number happens to be 0 to begin with. All right. How about this one? There's actually 2 different ways of doing this. Let's see which way you come up with. I hope I did it right. 0 to 3, 3 to 8, 8 to 5.
15.
Do you think the next one's 15?
No,
24.
Oh, I'm sorry, 15. I'm sorry.
24.
24?
35.
Yes.
48.
The next one would be
35.
35. The last one would be 48. How'd you do it?
Plus 3, 5, 7, 9.
Add 3 here, add 5 here, add 7 there. So therefore, we're going to think of
9.
odd numbers adding up. So this would be 9. So that would be 24. Add 11. This should be 35. Add 13. And this should be 48. Is that how I got the pattern?
No.
Want to know my way? This is the first term. 1 squared is 1. Take away 1, 0. 2 squared is 4. Take away 1. You get 3. 3 squared is, take away 1. 4 squared is, take away 1. 5 squared is,
25.
take away 1. So my pattern was squares. So the cool thing is, squares and adding up odd numbers becomes exactly the same, which is kind of cool if you think about it. All right. The last one I want to show you is one where very few of my students have ever gotten it. 27, 18, 12, I just want the next number. I'll give you a few seconds.
6.
9.
9. You get 9? How'd you get 9? I'm just curious.
3, 6, minus 9,
Minus 9,
minus 6,
minus 6,
minus 3.
minus 3. That is actually a valid pattern. So if this you subtract 9, if this you subtract 6, and here you would subtract 3, one of the answers would
4.
possibly be 9.
4
Where'd you get 4?
divided.
Divided by?
3.
If you divide 27 by 3, you get 9. But you're actually on a path that leads you into my pattern. My pattern is this. Divide 27 by 3.
9.
And times it by 2.
18.
Divide 18 by 3.
6,
Times it by 2.
12,
Divide 12 by 3.
4.
Times 2.
8.
8.
My number is 8. Now, which one's right and which one's wrong?
Both of them are right.
Both of them are right. Like I said in the beginning here, there probably is another pattern that will go 1, 4, 7, 10, and then possibly another different number. This is a good one because it shows you that patterns are not guaranteed. They put them on tests and they say find the best pattern. Usually the best pattern is the one that is the easiest to get to. So out of the two, which one is easier to get to? The 9. So probably like on an SAT, they'll be looking for a 9, and then I would have gotten it wrong because I put, because it's easier for me to see 2/3. It's just the way my brain works. All right, how about this one? 1, 1, 2, 3, 5, 8. Now, I was in graduate school. We were learning sequences. This is what these really are. They're called sequences. And our teacher gave us this problem, and me and 2 other people sat there for a half an hour trying to figure this out. I put it on the board in this class, and there's always someone that knows the answer, which is really cool if you think about it. That the pattern is so simple that for graduate students it was hard.
1 plus 1
So,
2 plus 1 is 3.
the next number is?
12.
Good adding, 13. The next number is 13. The next number is? 21. The next number is? 34. How do you get it? Well, 1 plus 1 is 2. 1 plus 2 is 3. 2 plus 3 is 3 plus 5. 5 plus 8. And so forth and so on. This is a very famous sequence. It's called the Adichie. More likely spelled wrong. It's called the Fibonacci sequence. Now, the Fibonacci sequence, he was a geneticist. He was studying how things reproduce. So he had a bunch of rabbits. So he started off with 1 male rabbit and 1 female rabbit. When you put them together, you have 2 rabbits. And then the rabbits get together and they have a baby. And then all of a sudden you have 3 rabbits. And this would be a model for population growth. And it actually worked out very well for him with rabbits. The cool thing is it applies to a lot of other things rather than just population growth. You know those seashells that have the circular pattern down to a point? I forget what they're called.
Conch. C-O-N-C-H.
C-O-N-C-H.
Conch.
So if you looked at the shell and you watched the pattern of that thing coming out, what happens is the distance between these, if you call that 1, then the distance between these 2 is 1, and the distance between these 2 is 2. The distance between the next one would be 3, 5, 8. It would follow that sequence perfectly. It's kind of cool if you think about it. So it became kind of a cool thing to come up with mathematically. All right, so those are our patterns. There are different types of patterns. They get a little bit more complex, but you'll have those on homework. Another pattern, is a game. Before the invention of paper, before it was easy to write things down in mathematics, before they had symbols for numbers, you still had to work with math. Like the Egyptians, they had taxes, they had to move stuff, they had to charge people money, so they had to do calculations for business purposes rather quickly. And to learn these games or to learn math without paper, think about that for a second. If you didn't have paper, how would you learn multiplication tables, addition, facts, division, all that fun stuff?
Some rocks.
Rocks are hard because then you'd have to carry them around with you. So most of the mathematical learning was verbal, just like stories were verbally transmitted from one generation to another. So they performed, little games to see if people knew their, operations. So here's a game. Pick any number that you want. Now, in this case, when I mean number, I mean a whole number, not square root of 3, pi, or we're not playing that game anymore. But it should work with all possible real numbers. So pick a number, multiply by 6, subtract 8, divide by 2, and finally add 4. So they'd let the students play this game, and they would let them play it with any number that they chose. All right, students, you're my students now, of course. Pick any number that you wish. I would highly suggest you keep it under 15. Otherwise, calculations get a little outlandish. Do not use your calculator, because the goal of this is to be able to do it mathematically using, what's in your head. Don't be boring and choose 1 either. 1. Choose a number, see what happens. I'll give you the 30 seconds. And I'm going to quiz you on that. Okay. DeVary, what you get? What did you
I
get?
ended up with 9.
You ended up with 9. You started with 3. What you get?
I started with 2.
No, I don't want to know what you started with. I'll tell you with that. You ended with 21 now. Or you better have. 15. You started with 5. You did too? What'd you get?
24.
24. You started with 8. I already asked. 30. You started with 10. So how am I figuring this out?
Multiply times three.
It's whatever you started with times 3 gets you to where you ended. So if you started with, what number did I not hear? 7. If you started with 7, multiply by 6, you should end up with 42. Take 8 away from that, that leaves you with 34? 34, okay. Divide that by 2, you end up with 17, and you add 4 to that, you end up with? So if you just went the shortcut route, you would say 7 times 3 is 21. Yeah, that's pretty cool. So my conjecture, now what is a conjecture? It is what you think is happening. Is it guaranteed to happen for all numbers?
No.
Not really, because how many numbers would I have to test? All of them, which is how many? An infinitude of possible values. So a conjecture is, I really think this is what's going on. I haven't proved it yet, but I really think this is what's going on. The conjecture is, the end is 3 times the number picked. There's other ways of saying it, but as long as you get the message across that whatever you pick at the beginning times 3, that gets you to the end. So this is what's called inductive reasoning. All of these patterns so far on this board fall into this category, especially with my pattern that had 2 different answers. You inductively conferred that the last number should have been 9, and I figured out it should be 8. We came up with 2 different answers, and there's a big reason that this is called inductive reasoning. It's not always true. Do you use inductive reasoning all the time?
Yes.
Heck yeah. You see things happening and you think they're going to keep on happening in that way. You hear a rumor and you believe the rumor to start with, don't you? Oh, so-and-so is sleeping with so-and-so. Really? You're all into that, yeah. But there's no proof that it's really happening. Only 2 people should know that it's happening. Unless they're kinky. Oh, come on. That was funny. Prudes. All right. So inductive reasoning is not the best way of going about things because you're never sure I think is absolutely true. Let me give you a couple little examples. The sum of an even and an odd number is odd. True? Absolutely true, or you conjecture that it is true? If you say absolutely, I'm going to say prove it. So I highly suggest you say conjecture. Highly suggest it. So you could test it out a few times, you know. Oh, an even number, 4, odd number, 7, add them together, you get 11. Seems to work for that one. All right. Pick an even number, 8, odd number, 3, add them together, you get 11. That seems very boring so far. So I can come up with a lot of these, and they will work. How do I know that it works all the time? You don't until you do something a little bit different than inductive reasoning. So what I want to do is prove this deductively. I hope I spelled that right. I'm not a very good speller. That's why I went for that. By the way, I could have taken this and proved it deductively without a doubt that this pattern works. So instead of picking a 7 to begin with, prove this deductively for all possible numbers. What represents all numbers? What can represent all numbers? N, like a letter, a variable. So if you chose n, you get n, and 6n, and 6n minus 8, then 3n minus 4, and then when you add 4, you end up with 3n, which is 3 times the beginning number. So to prove things deductively with numbers, you have to use letters. Yeah. So my question to you is, what makes an even number even? What makes an even number even? It can be divided by 2. That means the number originally has to be multiplied by 2. So all even numbers can be written this way. 2 times any natural number. N in this case is a natural number. 1, 2, 3, 4, 5, 6, 7, 8. Not all the rest of the stuff I taught you. So where n is natural. Okay. What makes an odd number odd? It's not even. And that's really important. To be odd, you have to be not even. Well, if this is an even number, what would be not even? 2n minus 1 or 2n plus 1, because an odd number is either 1 above it or 1 below it. But I'm not going to use n because I already used it here, so I'm going to write this as 2m minus 1. 2m minus 1. Okay. Now this says the sum of an even number and an odd number turns out to be odd. Okay. So I'm going to take these two numbers, even plus odd, and I want to see what happens to it. This is what's called number theory, by the way, where you start playing around with the ideas and numbers and proving things are true or finding that they are not true. You all took Math 70, right? Algebra?
No.
I have 2m and 2n here. What can I do? What's that called?
Close multiple.
Well, it's distribution, but when you go backwards with distribution, it's usually called factoring. You're going to factor out that 2. So if I kick out the 2, I'm left behind with n plus n. And then this minus 1 off to the end. Now, here's a really hard theoretical idea. Ready? If n is a natural number and n is a natural number and I add them together, I get a natural number. The sum of two natural numbers happens to be, well, natural. So I can rewrite this as 2 times p minus 1, where p is another natural number that happens to be n plus n. What? I just said that. If you have n and you have m and you add them together, you get a natural number. And I'm just saying that p happens to be the sum of m and n. That's all. Now, if 2 times a natural number is even, and I take away 1, it's guaranteed odd. So this is odd. Now, I can say without a doubt that the black statement at the very top is true for all natural numbers. Absolutely true, and it's called with deduction. With deduction. All right. How about this one then? Did you all take geometry in high school?
No, tell them.
Do you remember geometry? The biggest part of geometry was not, squares are squares, rectangles are rectangles, triangles are triangles. The biggest part of geometry in high school is proofs. Statements and reasons. You remember that, John? I'm not sure if they even teach most of what I learned in geometry. All geometry is built on is this deductive reasoning process. Being able to take two ideas that you know are true and proving other things about triangles and circles and squares and rectangles and all that fun stuff. So it's what's called a building process. So this is a building process of what's called number theory. That if you add an odd and an even, you get a odd. It's a small piece of it. Another possible thing is the sum of I gotta be careful of this. The sum of an even and odd number is prime. Is prime. Okay. What's a prime number? 1 is not a prime number. 2. The prime number is only divisible by two different numbers, 1 and itself. That's why 1's not a prime number, because it's not two different numbers, it's just 1. So prime numbers start off with 2, then 3, then 5, then... You know better than I do. This is scary. 31? I'm just curious if she gets stuck.
41, 42, 47.
Okay, I ain't got that.
Why not 51? You're supposed to get stuck around 31. Oh well. Most people get stuck around 31 and they start slowing down because they have to start checking the multiplication facts in their head. But would you memorize these? Scary. Very scary. So that's a list of the prime numbers. And over there, I already have 4 plus 7 is equal to 11, and 8 plus 3 is equal to 11, and 11's in this list, right? No, hold on a second. I only tested this twice up here, and you're all going, yeah, that's true. Tested it twice, it worked twice, so this must be a true statement. Well, here I've tested it twice, therefore this must be a true statement, right? It's not. It's not. Give me two numbers, one even, one odd, that is not a prime number. I'll give you a hint. Start with 6. Add 3. 6 plus 3 is? And 9 is definitely not a prime number. So this is what's called a counterexample. This proves that this statement is absolutely false. Does not work all the time. It has to work all the time. Here I proved it deductively. This one works guaranteed all the time. Here, all I had to do is show one that does not work. If at least one does not work, then the statement is false without a doubt. That's called proof by counterexample. Proof by contradiction is another way to say it. So deductive reasoning is, you have to be very careful. Inductive, yeah, you can get an idea of what's going on from certain numbers added together and see what ends up. But doing just two of them does not prove anything. Doing just two of them doesn't prove anything. It works great for this one because, well, this one was true to begin with. It doesn't work good for this one because this one was false. It might work some of the time, but it didn't work all of the time. You gotta learn how this works. You give me money when you're late. That's where I make my money. Oh well. Okay, so that's section 1.1. Now 1.3.
Are we skipping 1, 2?
Yeah, it's just estimation. We're not going to do that. Oops. Okay, this is problem solving. I guess you know the other phrase for this, which is called word problems. Y'all love word problems.
Nope.
Now, these are not like the algebra word problems where you had to set up an equation and then turn around and solve the equation. These are the types of word problems that you dealt with like in 8th grade. You take ideas and you try to figure them out mathematically. The cool thing about word problems is you need to know how to do that. Why? Besides me having testing you on them. When you get
Like part of life.
It's part of life. You get a job, your boss is not going to come to you with an equation for you to solve. They're going to come with a problem they want you to solve. They're just going to give you a bunch of words. This is what's happening, blah, 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 blah. I want you to fix it. And you have to figure out how to fix it. And that's the process that you need to go through. It's a step-by-step reasoning process that everybody needs to use at one point in their life or not. Steps. I worry about this part. There are steps that you can use to unconfuse yourself, or to at least get yourself in a forward-moving position on these problems. Too many people see a word problem, they just see words. They don't even read them. They see the words on a math test. What do?
Panic.
They skip it. They don't even read the problem. They see the word problem, they're like, oh, I ain't doing that, and they go on to the next problem. Because in their heads, word problems are difficult, impossible. And technically, they're really not. They're mostly common sense, for the most part. So step number 1, read the problem. It seems weird, but this is a step of solving a word problem. You have to read it before you can solve it. I do not allow you to turn in tests with blanks. You come to me with a test with a blank, I give it back to you and make you sit down. I don't accept blanks on any question on a test. You better answer everything. Whether it's right or wrong, I don't care. I want you to answer. There's no point in skipping stuff. So, read the problem. The second part of this first step is read it again. I'll give you a secret. When I read a word problem, the first time I read it, I don't understand it. I have no clue. Because it's just a bunch of words and the knowledge is just absorbing into my brain. So the first time I read a word problem, I'm a little confused. I don't care how simple it is. I don't care how hard it is. Of course, the harder it gets, the more confusion comes with it. But I don't understand it completely the first time I read it through. Sometimes when you read it through the first time, you read it way too fast. So the first time through, you're just getting comfortable with what kind of ideas they're throwing at you. When you read it again, certain things are going to start popping out. What's important? What's not important? What are they trying to figure out? Is there any other things I can do to make this a little bit more understandable? Sometimes word problems come at you and they have these huge numbers. And I'm talking like really big. Do you have to work with the huge numbers to figure out, what's going on? Yeah, you can make the numbers a little bit smaller, see how it works with smaller numbers, and then expand it into the bigger ones. Make the problem simpler for yourself. So, reading the problem the first time, you're going to be a little foggy about it. That's okay. Reading it the second time, you're starting to formulate what kind of ideas are really going on in there. If you have to read it a third time, no problem. I've done that before. I've read them 5, 6, 7 times in a row. By the 7th one, if I don't get it, I go ask somebody. Step 2. Make sure I do this properly. Organize the information. It's going to throw a bunch of things at you. You have to determine what's important, what's not. and how to get the things on your paper so that you can find information quickly. Now, some parts of organizing information include pictures. If they're talking about rooms or pools or decks or something geometric, draw a picture. Rectangles and circles, tracks, fields, anything like that. Sometimes you might need to write down a table to group information into columns or rows. They're also called matrices. What else? Tables, charts. Even if you just write the information down that's associated with one another close together, like price per pound and how many pounds. If you can get those two numbers next to each other, you understand that they really belong together. But tables do the same thing as that. 3, after you get all your information and you kind of have a clue of what kind of information they've given you, you have to figure out how it all goes together. So you need to decide on a setup. Setups can include formulas. You know, the famous one, distance equals rate times time, interest, I equals PRT, things like that. You could figure out some operations. Are you going to add? Are you going to subtract? Are you going to multiply? Are you going to divide? Are you going to do a combination of these things to figure out the problem? Some things to help you solve the problem. Make numbers smaller. And test. You know, see if it makes any sense by doing it the way you're thinking of doing it. Work backwards. Maybe the problem is asking you to go an unnatural direction. You're used to going left to right, and they want you to go right to left. Well, go left to right first and see how the problem works, and then it kind of gives you a clue on how to undo it. For instance, if you add 3 to a number going forwards, what would you do to go backwards? Subtract 3. So you do opposite operations. So it kind of gives you clues on certain operations. If you can figure it out forwards, you should also be able to figure out backwards. It's not that hard. Okay. Those are 2 possibilities. 4, solve it and get an answer. Go through your calculations, come up with a nice little number. Be careful. There are word problems where you get through the whole thing and you get x equals 2. But 2 is not the answer to the entire question. So you really want to go back and read the question. Make sure you are answering the question posed. If x equals 2 just becomes a part of the answer, like maybe x was your variable, but your length was 5 plus it, and your width was 7 plus it. You have to figure out what those other 2 numbers are by using the 2. And 5, check the validity. Validity, what's validity mean?
Make sure it's valid.
Make sure it's valid, make sure it's reasonable. I've had a word problem on a test before where I have someone driving 50 miles per hour and they're going out to the beach. How far is the beach from here? Maybe 200 miles, approximate, right? So they worked through the problem and they ended up with 7 hours. Now, if it takes you 7 hours to go from here to the beach, your car either broke down and you started doing about 5 miles per hour, or you were not doing 50 miles per hour, you know? So when you get down to the end, if you're using 100 cans of paint to paint a room, something is wrong. Your calculations, you just did something silly along the way. So make sure your answer makes a little bit of sense. I mean, that's where the common sense of this comes in. And a little bit with the deciding on a setup. All right. So let me give you a little sample. Which one's easiest? This one. It's kind of a silly example because everybody has cell phones nowadays, but oh A phone call costs $1.25. Oops. For the first minute. If you're at a payphone, this is what they do to you. They charge you a lot for that first minute and then a little bit less after that. I know. But you know, payphones, they're a ripoff. And for the first 2 minutes. 2 minutes. That's what I have written here anyways. And 32 cents per minute. For each additional. If you have $4, let's say you have like a credit card or debit card, you only have $4 on this phone card or whatever you want to call it. How long can you talk? Now, this type of word problem is the one that is going in the unnatural direction. You're not used to doing this type of problem in this direction. What direction are you used to? If I gave you that it costs $1.25 for the first 2 minutes and 32 cents for every additional minute, you're used to figuring out, if I talk 10 minutes, how much is it going to cost me? So probably the best way to deal with this problem is make up a number of minutes, see what kind of calculations you do, and then just go backwards. So let's see here. If you talk for, I better be careful. If you talk for 15 minutes, this is just a little side work, and it's just there to give us a clue on what this problem is really doing. So I want to talk for 15 minutes. How much is it going to cost me? What do I do? Nope. No, we're not going forwards, we're going backwards. So if I want to talk for 15 minutes, how much is this going to cost me? Well, the first thing you have to do is,
15 times 32.
I have to take out 2 minutes, and that's going to cost me $1.25.
Yeah,
It's just $1.25 for the first 2 minutes. And then after my first 2 minutes, how many are left? 13, and they're going to get charged by
32 cents.
So do I write 32?
What, 32?
0.32. If this is in dollars, this also has to be in dollars.
Cents.
So you have to write it as 0.32. If you want to talk about cents and you want to leave this as 32, that has to turn into 125.
What a 13.
Oh, I'm talking for 15 minutes, right?
Times.
But the first 2 minutes get charged $1.25, so that leaves me with, and that's why I like going forwards, because then the backwards I understand what to do. I gotta separate. So this is the calculation you would use to find out how much it costs for 15 minutes. I don't care what the answer is, but that's the calculation you'd use. So if I want to have $4 and I need to know how long it's going to take, what do I have to do? Well, the first clue is I got to separate those 2 minutes from everybody else. So the first 2 minutes, I'm guaranteed to be losing $1.25. So where does that $1.25 come from?
Out of your $4.
Out of my $4. So $4 subtract $1.25. That leaves me with $2.75. Now, the $2.75 has to handle the rest of the minutes. Now over here, I multiplied by 0.32. But because this was going forward and this is going the other direction, I'm going to divide by 0.32. So 0.32 goes into $2.75. Now calculators come in kind of handy. How many times does it go in? 8? 8.5? Give or take? A lot of decimals? 8.5. So, how long can you talk on the phone?
About 10 and a half minutes. No.
There's no about this. Phone companies are very precise. They'll take up
10
on it.
minutes.
10 minutes?
That's
8 minutes.
8. You
Think
got
about
those
what's going on.
first 2 minutes.
I got these 2 minutes over here.
So you're going to talk 10 minutes.
10 minutes.
10 minutes. know roughly about it.
10 minutes, you're just gonna talk 10 and you'll have some change left on your card.
I'll have some change left on my card. Will I be able to use this 0.5 of a minute?
No.
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 Not
Phone
if they
companies
charge
are
in
funny
minutes
because
You lose that.
you could talk for 10 seconds and they will charge you
or
for
entire
entire
minute.
minute. Once you go over that minute, it charges you for the next one. That's not enough to talk anymore. So the only thing you're going to get out of this is the 2 minutes plus the 8 minutes, and we're going to be able to talk for 10 minutes. And then they hang up on us. I'm sorry, no more money. So that's how I would do that type of problem. If I got confused what to do with the 2 minutes and the 32 cents, I would go forwards with it, see what calculations I did, see the separation of the times, and then just go backwards with every idea. Over here, we had addition. Over here, we had subtraction. Over here, we had multiplication. Over here, we had division. It's always going to be opposite operations. Compare forward and backwards. They're always going to be opposite. All right, that's an easy one. Let's get into the harder one. I like putting easy ones on the test because people screw them up. Because they treat them too easy. No, they treat them way too easy, or they make them just outlandishly crazy. And I mean, I've seen some views. Number 2. Let's see. Which one is it? No, it's not that one. Oh, it's the one they are. There we go. Number 2. Oops. Example. A room needs a throw rug, 1 foot from each wall. What's the difference between a throw rug and regular carpet?
Wall to wall.
Wall to wall touches the wall, goes right up to the edge of it. Throw rugs, they can just go someplace in the middle of the room. I want this rug to be perfectly 1 foot from every wall, so it's probably going to have to be handmade. Unless my room has nice dimensions and they make rugs the way I want them. Okay, the room is 20 by 15 feet. And the rug will cost $55 per square yard. $55 per square yard. How much will the rug cost? Now, why is this problem difficult? Well, it's dealing with a couple of weird ideas. Number 1, it's got geometry involved. Number 2, it's got conversions involved. You're converting measurements, and people do the strangest thing. I've asked before how many yards are in 1 foot, and someone has told me 3, which is kind of scary because they, in their heads, they see yards and feet, and they have that number 3 sitting there. This one's even worse than that because it has square yards. What's a square yard? How would you measure out a square yard on this floor? How would you measure it, though? You just cut it out? How do you measure exactly a square yard of this rug?
You step it up.
Well, you step it off. So how far would I go in this direction? A yard, 3 feet. And then I would turn it at right angles and I would go another 3 feet. Then I would turn it at right angles and go another 3 feet. And then turn again and another 3 feet. And that would be a square yard that's left in the ground. All right? So it's a yard on each side of a square. Therefore, a square yard. So when you're talking about a square yard, it is a square where each side is 3 feet. That's a square yard. A square foot is a square that at each side is 1 foot. Don't get confused between linear and area. Linear is just how far you go in a straight line. Area is how much surface are you talking about. Okay, the second thing about this is you're not just dealing with one rectangle, you're dealing with two at the same time. So my suggestion here is, if you're dealing with geometry, draw a picture. Here's my room. What are the dimensions of my room? 20 feet by 15 feet. If you draw a square, does it matter? Not really. As long as it's a rectangle, I could care less what the measurements are. Now, inside of this room is going to go a rug, and it's going to be nice and centered, 1 foot away from each one of the walls. That's a little bit harder to draw. But there's my rug. Here's my rug. Now, if I'm going to find the cost of this rug, what do I need to know about the rug? The measurements. I need to know how long it is, and I need to know how wide it is. So, how long is it?
20.
It is definitely not 20 by 15. Otherwise, it would be touching 19 by 14? Really? No. See, the problem is, you're losing the foot on this side, but you're also losing a foot on that side. 18. That's why the picture comes in handy, because a lot of people see that 1 foot and they only take it away once. But if you're in a rectangle, there's 2 sides to a length and a width. A left and a right, and an up and a down. So it's going to be 18 on this side. How much on this side? 13 feet on that side. So now we know the dimensions of our rug. Okay? If I'm buying a rug based on square measurements, I need to find what about the rug? It's area, the total square footage of it. How do you find the area of any rectangle? Length times width. All right. So the area of the rug is going to equal length 18 times width 13 gives you, I don't know, you all have calculators.
I have
234? 234 square feet. See, this was measured in feet, this was measured in feet. Feet times feet is square feet. So you get square feet. Notice how I read that. I did not say feet squared. There is no such thing as feet squared. It is square feet, even though it's written feet squared.
I have a question.
Go for it.
Okay, you saying like 18 right here
Uh-huh.
and everything. Why would it be 18?
Well, you started off with 20, and the rug is 1 foot from the right wall and 1 foot from the left wall. So you're losing 2 feet. So 20 minus 2 is 18, and 15 minus 2 is 13. Now, the rug costs $55 per square yard. But my room my rug is going to measure 234 square feet. I got to do a conversion. Ugh. Now, is it easier to go from smaller measurements into larger measurements, or easier to go from larger measurements into smaller measurements? Larger to smaller. Always easier, because you're just going to get more of them. If you go the other direction, you're going to get fractions of them, and nobody wants to work with a fraction. So, how many, and this is important, I want to change square yards into square feet. So I have this $55 per square yard. What I do is what's called unit conversions. Unit conversions. It's $55 per square yard. You say the word per, it's actually a fraction. The number in front goes on top, after the per goes on the bottom. It becomes a fraction. That's what per means. Like $5 per ounce. So it would be $5 over ounce. Yeah. It's just the way things are. Now, if we're going to do a unit conversion, we're going to multiply by another fraction. And it's really important. I want to get rid of square yards. So where I'm going to put square yards in this fraction has to be where it's going to cancel. So square yards has to go at the top. And what I want to convert it into has to go in the bottom. And that way, square yards divided by square yards, they cancel, which is, inverse, I think. You guys are algebra, so I won't worry about that. They cancel. And you're left with per square foot. Now, the problem is, I need to know how many of each go here so that it is equal, so that fraction is actually equal to 1. So how many square feet are in a square yard?
You have to divide by 3.
3? There's
It's
3
3 feet in a
linear
yard.
feet in 1 linear yard. That has nothing to do with square. Come back to my picture up here. It's 3 feet by 3 feet, right? So if I divide this into 3 feet each, that's 1 square foot, 2 square foot, 3 square foot. There's 9 of them. There are 9 of them. So for every square yard, there are 9 square feet. So 1 square yard is equal to 9 square feet. Now, here's a little tidbit. Very few rug companies sell by the square yard anymore. Most of them have switched over to square feet. So they would have a price, $55 per square yards, and they might make it $20 per square foot. Why do they do that? Well, because most people think there's 3 square yards or 3 square feet in 1 square yard. They divide that by 3. They find it's 20 doesn't sound like a bad deal, but they're ripping you off a lot, because then they're changing it into 180. 9 times, what did I say, 20? Yeah, $180 per square yard rather than 55. So they did the conversion into square feet to be able to raise the prices even higher. Because people don't understand you're supposed to divide by 9, they use 3. They take advantage of people's math skills. I was watching Candid Camera once when I was a kid, and they had a table set out in a mall, and the sign said 110% off. And people were going up and going, how much do I owe you? It's 110% off.
Nothing.
You buy everything on that table, and they give you 10% of the cost. It's 110% off. 100% off is free.
Yeah.
So 110% off.
They owe you some money.
I'd be like, give me it all. Give me it all. But people, well-dressed people, are going, how much do I owe you? Crazy. So businesses will take advantage of your math skills. The math skills of Americans is crappy. It is beyond poor. Have you gone to the grocery store? They had to put on, by law, price per ounce, unit price. And what I found was when you were buying sodas, Coca-Cola was price per pint, and Pepsi was price per ounce. So you couldn't even compare the unit prices because one was in pints and the other one was in ounces, unless you knew how many ounces were in a pint. And I have no clue. I think it's like 16. I'm guessing. It might be 32. I have no idea. But again, they're taking advantage of our math skills are not that good. I think a new law passed where they have to be exactly the same. All the products, if they're measured, if you have toilet paper, it has to be per square foot, per square foot, per square foot. They can't change the measurements. All right, we're not done with this problem yet. How do I find out how much this rug costs? Well, I got to find out that unit price. So let's see here. The square yards are gone. One's on top, one's on the bottom. That unit of measurement goes away. What do I do with the 55 and the 9? It gives you a guaranteed operation. One number's on the top, the other number's on the bottom. You better divide. Oh. Carry. Okay, so what's 55 divided by 9? I need it in money, so it's going to be dollars. $6 and 11 cents per square foot. Per square foot, because that's the only other measurement left. It's in the bottom, per square foot. That's not bad. Now, what do the rug stores do? They sold it for $55, they start selling it for $8. And you're thinking, oh, that's a deal. And actually, you're getting ripped off $2 per square foot. Okay, so now what do I do with the 611? I'm going to multiply. So I'm going to take my $6.11 per square foot. I'm going to keep that in here. And I'm going to multiply it by 234 square feet. The cool thing about keeping the measurements in there, I know you weren't taught to keep the measurements in there, you were taught to get rid of them. But if you leave them in there, you see what happens. What happens in square feet? And all you're left with is money. And that's what you want, is just money. So $6.11 times 234 gives us a grand total of $1,429.74. 1,400. Huh?
1430.
1430? 1430. Even?
No, it's 1429.
Oh, well, $14.29 and 74 cents. This is how much it's going to cost you. I guess you can add in a little bit for tax. It's going to be a lot more than that, though. How would you find tax? Times it by, well, I think it's 0.065. Is it 7 now?
It went
It went up. 0.7. And then add that into the price. All right, so that's the rug problem. See where you can screw up. Thinking that you're only taking away one, working with square yards and square feet and thinking there's only 3 square feet for every square yard. It's a lot of little pieces. What time is it? Ooh, I got time. How about this one? A faucet is leaking at a rate of 1 milliliter per second. Every second, 1 milliliter of water is dripping down here. I think, no, make it 0.1 milliliters. 0.1 milliliters per second. So it's like drip, drip, drip. Can anybody sleep through that?
No.
I can. Oh, it annoys the heck out of me. Probably because I know about this problem. How much water will be lost per year? We have this dripping faucet. We can sleep through it, so we ignore it for an entire year. How much does it cost to fix a leaking faucet? About 10 cents. You go to Lowe's, you get the right size washer, you take the thing apart, you put the washer in there, you put the thing back together, you're done. 10 cents in about 20 minutes. Okay? So we have this 0.1 milliliters every single little second. I need to do 2 conversions. Number 1, milliliters is, or 0.1 milliliters is a very, very small measurement. Milliliters is kind of a small measurement. I need to change that into a little bit larger. So what would be a better one besides milliliters? Liters. There's 1,000 milliliters for every liter. The other measurement I really got to change is seconds, because we need to change it into years. So this is a major unit conversion. So the first thing I'm going to do is change, let's change milliliters into liters. That makes the number a little bit bigger. Not much though. So we're going to get rid of milliliters, so that goes in the bottom. We're going to change it into liters. That goes in the top. There are 1,000 milliliters for every single liter. There's 1,000 milliliters for every single liter. All right. Oh, maybe I don't want to do that calculation first. Why? 0.1 divided by 1,000 is going to make the number really small. So I'll leave this here, but I'm going to change that number in front first. So we'll come back to him. I don't want to go that direction. So 0.1 milliliters over seconds. Let's get rid of the seconds. Okay. So if I'm going to get rid of the seconds, that's going to go up top. What am I going to change them to? You cannot change. How many seconds are in a year? I don't know. Minutes. Minutes. So how many seconds are in a minute?
60.
All right, so 60 seconds in 1 minute, a year. Mr. Eric would know. He probably does. He probably knows his age in seconds. All right, now we want to get rid of minutes, so he goes in the top. And we're going to change minutes into hours. There are 60 minutes for every single hour. Then we want to get rid of hours. Change it into days. How many hours in a day? 24 hours for every single day. Oh, I'm running out of room. Well, you write next to this times, and I'll write it down here. Times, I want to get rid of days, so that's going to go up top. And I want to change it into?
A month?
We can go to year, kid. How many days are in a year? We can go right to a year. A year. There are 365.25 days in a year.
And this is what I need.
We're catching up on it this year, right? February has 29 days rather than 28. So 365 days per year. So what happens? Well, the seconds are going to go away. The minutes are going to go away, one on the top, one on the bottom. The hours are going to go away. The days are going to go away, one on the top, one on the bottom. And when we're done, this is going to be milliliters per year. What operation do I use between all of these numbers? Multiplication, because all of the numbers are on the top. So, what's 0.1 times 60 times 60 times 24 times 365? Yeah, that's why calculators were invented. For numbers that you do not want to calculate.
52,000.
No.
3,000,000.
3, 1, 5, 3, 6, 0, 0.
I missed out somewhere.
Yeah, yeah. Make sure you can type those in and get that answer. What's the measurement here? Milliliters per year. So this is milliliters per year. Wow. That's 3,153,600 milliliters. God, I don't know what that is though. So I'm going to come back over to this side. Instead of 0.1 milliliter, I'm going to replace that with that number. 3,153,600. That's nicer to divide by 1,000. It's actually easy to divide by 1,000. All I have to do is move the decimal 3 times. I don't need a calculator for that. So the answer here is going to be 3,153.6 liters per year. Per year. I'm still not quite sure what that really means. What kind of volume in liters do we understand a lot about?
2 liters.
2 liters. I know how many 2-liter bottles. So how many 2-liter bottles is this? Well, to find out how many 2-liter bottles, you just take this and cut it in half. So how many 2-liter bottles of water did we just lose for the whole year? 1,000. I'll give you that much.
576.
576. 2-liter bottles. You have lost. Just think about this for a second. You take a bunch of 2-liter bottles and you start pouring it down the drain. You have to dump 15, almost 1,600 of them down the drain.